Chapter 5. At this point, you have to turn back on your this is on the exam brain, okay? So take a deep breath. You have to know this stuff. This is not going to be mathematically difficult. Conceptually, it is difficult, all right? The math will be easy if you can get the problem set up. Also, look, it's our friends again. Now he's wearing blue, and I think he's a completely different person. And here he's got a black eye, apparently. And I don't know who draws these things. I feel like there's like one person, and his whole job is to draw dudes that are just kind of like random dude, and that's just what he does. I don't want that job. That sounds terrible. All right? So, relativity. Relativity. First of all, the first thing you need to know about relativity is that it breaks down into two broad categories. It's going to take us today and Wednesday to deal with the first category, which is known as special relativity. Special relativity. I'm going to talk about that a lot in detail. We're going to do example problems. It's going to be fantastic. You're going to kind of maybe weep a little bit at the world in which you live, and then we'll move on to general relativity. General relativity is the other category. It is mathematically intense, and we're going to do very little with it, okay? It takes extra stuff beyond the math requirements you have in this class to deal with general relativity, so I'm just going to describe the concepts when we get there. That'll be what we do probably on Friday, but most of our discussion is special, okay? Our discussion is special. It is a special discussion, all right? You are going to see that special relativity is going to be built on some really, really, really basic ideas that lead to really profound implications. So as we go through these thoughts, this is kind of how things are going to feel. You're going to be like, oh, duh, okay, huh? Like, it's like, did I miss something? Like, did I just fall asleep for 4 slides? How did we get from point A to point B? Because these concepts are so basic, but then, like, it completely gets ridiculous really, really fast. Okay, so prepare yourself for that. What is special relativity? Special relativity was published by Einstein, 1905, and it completely changed our understanding of those things. Time, changing our understanding of time. That's a big deal. Length, well, that's a really basic, like how big is something, like making measurements of something. And then more complicated things like mass and energy. It completely upended everything about those. What is meant by special? Special refers back to something we talked about last semester just a little bit. Special is that it only applies if I have inertial reference frames. Inertial reference frames mean that the world that we're studying is not accelerating. I'm trying to remember where exactly we dealt with that. Does anybody recall? I know I've had this discussion with you guys. What was that? Something? Yeah, there was some rotation stuff and the Coriolis force. Yeah, some of that stuff. I think we talked about it earlier too, maybe twice last semester. I can't remember exactly. I think also with Newton's first law. Newton's first law, we discussed non-accelerating reference frames. Essentially, inertial or non-accelerating reference frames are where Newton's laws are obeyed. In other words, Newton's first law said that if something doesn't experience a net force, it's going to keep doing what it's doing. If it's moving at a constant velocity, it'll just keep doing it. If it's stopped, it'll just keep doing it. It's the idea that if you're sitting on an airplane and it's moving perfectly with no acceleration in any direction, if I set something on the tray table, it just stays there unless somebody comes along and pushes it, right? An accelerating reference frame would be in the plane when all of a sudden it's like, and we start speeding up, and then all the stuff on the tray table goes blah and falls in your lap. That stuff moved without anybody pushing it, right? All of a sudden Newton's first law was broken. It didn't operate appropriately. That's the difference between inertial or non-accelerating and non-inertial or accelerating reference frames. So all of our discussion here is in a world where constant velocity is happening. Good so far? Okay? When we get to general relativity, it's going to include this and let things start accelerating. That's the primary difference between the two. So special is like a subset of the overall thing. It's special because we have to have non-accelerating reference frames. So the two basic ideas that Einstein had that led to some ridiculous stuff. The first one was the equivalence of physical laws. Essentially, the laws of physics have to be the same in every reference frame that's not accelerating. And they illustrate this here with a diagram. See this little guy right here with whatever experiment he's doing. What is he doing anyway? Looks like a mass and a spring. He's like doing a physics 8A lab, essentially. For some reason, on the space shuttle. See, there he is. He's on the space shuttle doing a physics 8A lab. I don't know how he got the funding to do that. And the space shuttle is moving with a constant velocity to the right. Okay? So he does an experiment there, gets some results, writes a lab report. It's terrible. He hated the whole thing. And then he decides to land the space shuttle. How can he do all that? Wow, it's really impressive. And he lands it, and he goes like to the tarmac, and he's on the ground, and he does the exact same experiment after changing his shirt. And he gets the exact same result. So it doesn't matter if you're at rest or at constant velocity. As long as you're not accelerating, you should be able to do the same experiment and get the exact same results. I think that's kind of a duh idea, right, to begin with. It's like, well, yeah, that should happen. Again, like I talked about last semester, if you're riding in a car, like tossing an object up and down, you expect it to have the exact same result as it does if you're standing on the sidewalk, right? You toss it up, it comes back down into your hand. I stand on the sidewalk, I toss it up, it comes back down into my hand. It's not different in the car at constant velocity. It doesn't go bloop, boom, hit me in the face, okay? You expect them to be the same. What Einstein did was say, okay, let's take this idea and say that it also applies to EM waves. In other words, he decided to say, like, this isn't just for Newton's laws. It's just not for a ball that I'm tossing up and down. But if I turn on a flashlight or a laser, which didn't exist at that time, or do something with light or any experiment, I still have to have equivalence, whether I'm in that non-accelerating reference frame or this one. It needs to apply to everything. So that's kind of the first little twist on an idea that we should already understand. Equivalence of physical laws. Are you good with the first one? Yes? 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 Yes. Hey, that was to shut me up, wasn't it? It's like, we'll say yes, then he'll stop. So, let me ask this first question. Which of the systems to the right are not inertial reference frames? Your question. He is applying it and saying that if an experiment is done with an EM wave, the same results should happen in any reference frame that's not accelerating. So you could kind of go back to this and replace this guy with like a laser, and he's doing some other kind of experiment. Excuse me. He should get the same results in the space shuttle and on the ground too. Well, but he is moving. He's just moving at constant velocity with respect to the people on the ground. Okay? What's the answer over here? Anybody? The third one is not an inertial reference frame. Why? Because it is accelerating. Circular motion has centripetal acceleration. That one doesn't count. So if you do an experiment on a merry-go-round rotating at a constant rate versus one on the ground next to it, you can expect some different results. And we saw some of that with some of the forces we looked at in a rotating reference system last semester. Don't think about it too much. It's okay. Person standing still, person in an airplane in mid-flight at a constant velocity. We're assuming since it's in mid-flight. Both of those are good. Those are inertial reference frames. Okay? Number two. So, first thing is that we have to have the exact same results no matter what inertial reference frame we're in. Number two is I get a drink of water. So you just have to wait a second. It's good. It's good water. It's not coffee, but it's good. I'm going to have another one, okay? The second one is the constancy of the speed of light. Again, these two ideas are Einstein's. He's the one that's putting them forth in this paper in 1905. The constancy of the speed of light says that the speed of light in a vacuum is the same in all inertial reference frames, regardless of what's happening with the people doing the measurement. So it doesn't matter whether the thing that's emitting the light is moving. It doesn't matter if the person receiving the light is moving. As long as both of those reference frames are moving at a constant velocity, they're not accelerating, they should measure the exact same speed for light. And of course, we know that to be 3 times 10 to the 8th meters per second in a vacuum. So last semester, do you remember the idea of relative velocities? It wasn't quite right. It worked for what we were doing, but at the end of the day, we need some extensions on that. That'll happen in this chapter. The idea was, if you look at, let's just get rid of this. I don't like this diagram, so I'm going to make it go away. There's too much confusion there. Look at A and B. We've got someone in a boat who is traveling into some waves. So imagine these waves, this is velocity of wave in the water, is coming toward him. It was created by something else, and he has a velocity moving to the right in the wave. If he is to measure the velocity of that wave, what's he going to measure? What's he going to get? Yeah? Are you sure? Think about it one more time. You're close. If it helps, think of, let's let the velocity of a wave be another boat coming in your direction. And it's moving at some velocity with respect to the water. And now I'm traveling at the boat, and the boat is coming toward me. What are you going to measure for the velocity of the boat? You add them. Exactly. Thank you. So if this person measured the velocity of the wave, they're going to see it as v plus the independent velocity of the wave. They're added together, right? And this is just regular Newtonian relative velocities. We did that even in 2 dimensions last semester. You just add them together if they're going toward each other, okay? On the other hand, if they're moving away from each other, so now this guy's moving to the right, and the wave is going away from him, and now he decides to measure the velocity of the wave, well, he's going to get velocity that he's going minus the velocity of the wave, okay? If you're not good with that second one, think about what you would get if he's traveling at the exact same speed as the wave. What would the answer be? 0, right? Which sort of makes sense. It's like he caught up with the wave, and now it's like, hey, me and the wave are going together, so he looks out and he's like, how fast are you going, wave? Like, you're right there. I'm not moving at all, okay? Think of it as like you and another car on the highway, both of you going at the exact same velocity. Relative to each other, you perceive 0 relative velocity, versus you and a car coming towards you have additive velocities. You perceive them as coming extra fast because your velocities are adding together. Let me get this out of the way first. You see the idea, you see the concept, your question. That would be like if we were stepping aside trying to find, a net velocity or something. We're specifically looking at the velocity of the wave relative to the person in the boat. So how does it compare to them? What do they see the velocity of the wave as? Yeah.
And if velocity is a vector, doesn't that make the addition actually subtraction?
Doesn't that make the addition actually subtraction? Well, we're not adding these two together, really, as separate vectors. Instead, we're adding Oh, that's a good question. I should write this out more explicitly. Ooh. Velocity of wave with respect to boat equals that. So it's another third velocity. It's not that one or that one being added together. We're finding a third velocity that's not drawn in the diagram itself. Okay? Velocity of the boat with respect, or the velocity of the wave with respect to the boat. Okay? We're adding the magnitudes, yeah. So if that helps as well, let's do that. Okay? So if it helps, put yourself in a car, again, and think about these different ideas. For whatever reason, they used boats because you could have waves on the water, and we're about to deal with light, which is a wave. It's not the best idea, but I get why these figures are using water waves, all right? So the thing was, people thought that, well, maybe this applies to light as well. It's like, okay, fine. If I do the exact same thing with light and measure the velocity of the light wave, maybe these same equations would apply. In other words, if I'm in the car and there's some source of light being shot at me, and then I'm going into the light and then measure the light wave, it should be the velocity of me plus the velocity of the light wave. It's like it's coming at me. I should experience it as faster. On the other hand, if I'm going this way and someone shoots a light ray next to me, like as I speed up, it would make sense that I could like maybe catch up with the light wave at some point, like kind of like I did with the car next to me, so that I would perceive it as going with zero relative velocity. It turns out that didn't work out. Okay, so you remember this dude Michelson? Like we talked about him in respect to another experiment. Okay, they tried to see if they could measure different speeds of light in a vacuum based on the Earth's motion around the sun. Like you could imagine, like, ooh, sometimes light from that star, I'm going directly toward it on the Earth, and then in the other part of the rotation, I'm going directly away from that particular star. Maybe I can measure a slightly different speed of light in a vacuum based on that. They tried and tried and tried to no avail. C was always C, exactly. Many more experiments have been done since then with more accurate equipment because, late 1800s, like, you kind of wonder what their precision was. Since then, this has been verified over and over. No matter what is happening, the exact same speed of light is measured, which means that we have a little bit of an issue. Hey, look, it's another random person. This one's kind of boxy and weird. I also feel like with all these diagrams, they kind of built in quantum ideas a little bit. Like I can't really tell exactly where he is. He's a little bit fuzzy, right? It's kind of wavy right there on the arms. Yeah, I think so. Can't really tell what's going on. Is this the same person? No. Wow. That is one ominous guy. I'm going to zoom out of that, okay? So here's what we're saying is happening with light. Notice there's a truck, or a Jeep, I guess, that's shooting out a beam of light at the speed of light. And then you're just standing there on the side of the road, maybe making a speed of light measurement, as one does, right? Yeah. You might think like, well, let's see, the Jeep is moving at velocity v, and then shoots a light beam at c. Well, I should measure the speed of light as what? Should be c plus v. Let's say that I can throw this pencil at 10 meters per second, and I can run at 10 meters per second. Yeah, I'm not so sure about that one, okay? And let's say you are over there at the wall, okay? All right, let's say I don't run, and I'm just like, 10 meters per second. And you're like, how fast did it hit me? 10 meters per second. Now, what if I do the same thing running, right? I'm running at 10 meters per second, which I'm not going to demonstrate. How fast is the pencil moving while I'm running? Yeah, and then I throw it. It would make sense then that, like, my velocity is already on the pencil, and then I throw it at 10 more meters per second. It should hit you at 20 meters per second, right? That's what's happening here, just with a lot faster things. It's like the velocity of the Jeep plus throwing the light at c those should add together based on what we said on the previous slide. Yeah? Okay? On the other hand, if they threw the light the other way, it should subtract. These are regular additions of velocities. The thing is, that doesn't happen. Let's switch colors here. Doesn't work that way. Instead, in both cases, C is measured. No matter how fast the Jeep is going, the person always measures the speed of light as C, 3 times 10 to the 8th meters per second. This is the equivalent of doing what we just did with me and the pencil throwing it at you. And if I'm standing still and throw it at 10 meters per second, you're like, whoa, 10 meters per second. If I'm running at 150 meters per second and throw it at you, you say, oh, 10 meters per second. That would be weird. Do you not agree? And it doesn't make any sense. In fact, maybe I have the ability also to detect how fast I throw it. And I'm like, look at this. I can throw it at 10 meters per second. Here I go, 10 meters per second. Whoa. And then you're like, good, 10 meters per second. And now I'm running at 150 and once again say, here we go. I threw it at 10 meters per second, and you say, I agree. You threw it at 10 meters per second, even though you were coming at me at 150. That doesn't work in our physical world. Yeah. How is that the same as what we just did? Let's see. That is the same as... yeah, it's bothersome, isn't it? These examples just don't fit together. It's the same idea, but it's expressed in the backwards direction, and I don't care for that. So if it... Yes?
I guess for this one, you're measuring it and you're going that way, but the other direction, you're just standing there and you're measuring that.
Yeah. I can understand it being convoluted. If it helps, replace this totally with the pencil and me running, and just ignore this completely, and it's okay. All right? Because it's like trying to explain the same concept in the backwards direction, and that is confusing. And I'm sorry for that. Yeah. Put the person in the car, this person, and then... Yes, I agree. It would be the same if we put the person in the car. I need to change that previous slide next go around. Yes? Maybe? Okay. I think I completely agree. So, notice the extreme example down below. We're taking this even farther, okay? Hello. Can I help you? Let's look at the example down below. We have a person on the ground, we have a beam of light, and we have a rocket, okay? This is all the way to the extreme, though. So we imagine that both of them are observing a beam of light that's going past them, and we're assuming that number one is just standing there. They make the measurement, and they say, oh, I measured that beam of light. It's traveling at 3 times 10 to the 8th meters per second. Okay? The person in the rocket, let's say that they can go way faster than anything we can currently conceive of. We're saying they can travel at 90% of the speed of light. Based on what we said on the previous slides, we would expect them to be catching up, right? It's like now, relative to the light, you would think ooh, light's only going 10% faster. They should kind of see light as going slower at this point. The thing is, they make a measurement of the speed of light and see the exact same thing. They're like, look at the light go, 3 times 10 to the 8th meters per second. How could that possibly occur? The flash, huh? Yeah, not true. Yeah, because still, all the light coming off the objects is going to be coming at the exact same speed. Yeah, I'm sorry. Yes, quit watching The Flash, apparently. The whole DC universe, just throw that out and stick with Marvel. That might cause problems. I should take all of that back. All right, let's see. So, notice we're dealing with a great rate of speed here. In general, if we're traveling at normal, everyday velocities, just using regular addition of velocities works totally fine. We don't notice any of this. The thing is, as we deal with higher and higher speeds, like rockets that are traveling at some percentage of the speed of light that's not negligible, all of a sudden we have to use Einstein's theory of special relativity, which works for slow speeds and high speeds, and not just regular old addition of velocities like we were trying to do with the boat or with me and the pencil. Okay? Let me show you what is happening by, hold on, how many of these questions I have? Ooh, let's do these first, and then we'll deal with more fancy things in a minute. Can you read that? You are in a spaceship with no windows, radios, or other means to check outside. I'm sorry, you're apparently in a space prison. That just sounds bad. How would you determine if the spaceship is at rest or moving at a constant velocity? I'll give you a chance to read all the options. I'm going to have more water. You don't have a precision watch? I don't know. So this is one of those times where what sounds like the ridiculous answer is actually the correct answer. Keep in mind, based on the first basic idea, as long as I'm in an inertial reference frame, all experiments should behave the exact same. And notice it says we're trying to compare between at rest or moving at a constant velocity. Those are both inertial reference frames. I can't detect the difference. It doesn't matter what experiment I do. Devise whatever fancy thing you want to do, whether it's, let's go back, and you wanted to, play with springs and masses, or you want to shoot lasers and do some fancy experiment. Nothing's going to tell you the difference. Your space prison could be doing anything except accelerating, okay? Anything else is perfectly valid. So let's look at I can't slide over. The next case, where we're going to go a little sci-fi. Hello. No worries. You know of the Borg, right? No? Yes, some of you. They had spaceships that were just cubes, but that's not a terribly wonderful representation of a Borg spacecraft. It should be more like, there we go, that's a little better. The Enterprise is traveling at 75% of the speed of light toward a Borg spaceship approaching at 75% of the speed of light. If you didn't know anything about this special theory of relativity and you were to ask Sir Isaac Newton how fast the Borg ship is approaching, what would he tell you? That's like being in the Enterprise and, how's that happen? And you're trying to measure this thing coming at you. This would be like you're in the boat, yes. Or maybe we decide that I'm going to run this way at 10 meters per second, and you're going to run toward me at 10 meters per second. How fast are we approaching each other? That would be 20 meters per second, essentially. I would detect you as coming at me twice as fast. So what would this be based on old principles? It should be 1.5 times the speed of light. Okay? So each one's going at 3/4. You should get 1.5. Yeah. So if you were, yes, yeah, that would be an equivalent case. Let's do the next one of these. Same case, Borg Enterprise. And you think we're doing sci-fi math now, right? We're using sci-fi examples because we can't go this fast, but the same principles apply. So now you're deciding, like, I know about relativity, and you're going to tell Newton the way things really are. That feels like a powerful position to be in. What would actually be the answer? You know that this one's no good because we know that the things don't just add like we might expect them to. And I may have to tell you this answer because we don't quite know enough yet. Any thoughts? Number one? Seems like maybe it could be number one. It's not. But maybe it could be. Maybe 5? More? It's like, it kind of makes sense like I'm adding the velocities together, but not all the way together because something weird is going on. I would agree with you. Number 5 is the answer. But we're going to have to learn a little more about the math to get to that more precisely. None of these are going to work out, and I'm going to show you why on Wednesday. We're not going to be able to get to that today. And I think I have one more of these. We'll do this question, and then we will deal with the details next class. In the Enterprise, at half the speed of light, again, heading toward a Borg spaceship. You got to hate this. By the way, you're not going to get away. Resistance is futile. You can't escape this situation. You fire your phasers, which are beams of light, essentially. Light, there we go. And you see the light waves leaving your ship at the speed of light c toward the Borg. What does the Borg experience coming at them? Yeah. So even though there's this relative velocity between the two, like you're traveling at half the speed of light, and now you throw something at the speed of light, they do not see those two velocities added together. Instead, all they experience is light coming at them at the speed of light because of its constancy. We'll deal with that in more detail next time, and this one, which has great answers.
It seems. So before we get into sort of the meat of things, let me go back and rehash the two basic ideas that we're talking about. First of all, that no matter what inertial reference frame you do a physical experiment, you have to get the exact same results. This is known as the equivalence of physical laws. It doesn't matter if you're on the airplane or on the ground. If you're moving with constant velocity, it's an inertial reference frame, and you should get the same results. Second of all, no matter what inertial reference frame you're in, you should measure the exact same value for the speed of light in a vacuum. And that doesn't matter if you're moving really fast directly at the light, you still measure c, just as if you were sitting still, which is a weird notion. Nobody really likes it up front, but all experiments show that this is true, which you got to admit, if you were Einstein, who's coming up with this, like he's not doing experiments, he's just speculating, this should be true. Wouldn't you like to be able to just say something should be true and then be proven right for the next 100 years by all subsequent experiments? Yes? You get the same. The same. Yeah, I mean, with any measurement, there's going to be some experimental error, but there's not a drift outside of that.
So even if you're on, like, in the boat or outside of the boat, whatever measurements you do, you're getting the same value.
Yeah. Okay? This leads to weird things. How do you measure velocity? What are the two things that you're going to have to measure to calculate a velocity? Distance and time, right? So velocity is distance over time. If I'm moving with respect to the thing that I'm measuring and someone else is not moving with respect to the thing that we're measuring and we get the exact same result, well, that means something's wrong with distance and time. Both of us are saying, ooh, look, the light traveled a certain distance. It took a certain period of time. I got 3 times 10 to the 8th meters per second. Someone else measures the same exact two things, and it divides and gives them the same thing. That means for those two people, something about the distance and time has to disagree such that they can end up getting the same result. It turns out it's both of them. both distance and time are kind of screwed up by this whole idea of the constancy of speed of light. So let's go over and talk about this slide. I think that this whole thing here is kind of pointless, so let's just get rid of that. All the answers are kind of pointless as well. So let's get on with things and talk about the effect that these two principles have on our concept of time. So there is the idea known as time dilation. Time dilation says that moving clocks, and notice there's quotes around that because we use clocks to measure time, but we're not necessarily just talking about clocks, run slow compared to clocks at rest. Moving clocks run slow compared to clocks at rest. Now, maybe it would be better to say that moving clocks measure time in a way that is more extended than clocks at rest measure time. Because I don't want you to think like, oh, I've got like a clock, and when it's moving, there's something about its mechanical parts that kind of get shaken up, and like it doesn't work quite as well. It runs slow. It's not a mechanical, physical thing. It's literally that when they measure time, they get a different value. They would say that the moving clock says more time has passed compared to the clock that's at rest. Dilation is just a fancy word for stretched out, extended. Time dilation means stretched or extended time. We can use a really basic idea for a clock that we see in these two diagrams to start to get a feeling for why this has to be true because the speed of light is a constant. So again, this is happening specifically because c is constant in all inertial reference frames. So we're going to invent what we might call a light clock. Okay? All clocks are really based on some repeatable thing that occurs at a regular interval just to tick off seconds or whatever interval that you want to. Yes?
The clock is not the clock you associate with everything.
Sure. Yeah, that's totally fine. This wouldn't be terribly handy as a wristwatch, but same idea. Clock measuring time. Yes. All right? So this light clock is going to measure time with a beam of light. All it consists of is a mirror at the top, a mirror at the bottom. There's a source of light, and it's just going to shoot a beam of light straight up and straight back down. Okay? That's it. Maybe imagine that distance d is very precise, such that when it goes up and back down, that's 1 second, if that helps. It could be any arbitrary length of time. So someone has built and constructed this based on the speed of light so that every time it goes doot, that's like tick-tock, right? It measures 1 second. Now, based on the speed of light and our velocity equation, velocity is distance over time, if we wanted to do a calculation of how much time this takes so we could build our clock to get the exact right distance, well, let's see. How much distance does it have to cover to go up and back down? It looks like they're saying d is 1 trip up. So in this particular case, the distance covered is 2d. We don't know how much time that's going to take, but since we're dealing with light, we know the velocity is c. So just rewriting the equation in terms of this imaginary light clock that we've made, okay? Light travels at a certain speed. It's got to go 2d up and back down. That's going to take a certain period of time. Let me pause for a second. Yes? Clocks measure time. Clock. Yeah. Any clock. It doesn't look like a clock. Yeah, but you could extend this idea to literally anything that we use to measure time. We are basing it on light to help illustrate the effect. Okay? It's going to help draw out why the speed of light matters. Your question.
A moving clock would be a clock that keeps time, and the resting clock would be...
Not there yet.
Oh, okay.
Not there yet, okay? So when we say stationary light clock, it's like literally I put 2 mirrors like this. I take a laser maybe that can pulse a beam of light, and it's literally stationary. And we've built it such that when the light goes up and back down, it's like maybe there's something over here to the side that says 1 second. And then the light goes up and back down again, 2 seconds. And it's literally going to measure time. Maybe it's the time of day, maybe it's a stopwatch, depending on how you decide to configure it. So it's literally a different type of clock, but it does the same thing that all clocks do. Okay? So when we decide to have a moving light clock, this is not hands on a dial that's spinning. It's not anything other than now maybe my clock is on wheels. And I decide to say, let's push it. Now it's a moving light clock. It has a velocity to the side. One is stationary compared to us. Like we look at it and we say, it's sitting still. One is moving relative to us. We say it's going across the tabletop. Okay? Are we still all right? Imaginary clock. One's moving, one's not. Question.
When you say relative to ours, do you mean that, like, if we're moving at the same velocity that the clock is technically not moving?
Then it's technically not moving.
And so it would be the same as station.
Yes. All right. So we're assuming everything is relative to the classroom and to you guys who all appear to just be sitting stationary relative to the classroom. Okay? Now think about what happens. Look at that beam of light at the bottom. This right here is one light clock. Okay? So maybe imagine there's a little detector that's right here, and it's trying to shoot the light straight up and back down, but it's going sideways. Right? So by the time the light goes up and back down, the clock's not in the same place anymore. Right? So it's like it shoots the light up here, and then by the time the light reflects and comes back down, the entire clock is over here somewhere. Agreed? Think about this. I'm tossing a ball up in the air. If I'm standing here and I just go, maybe that takes 1 second. Okay? What happens if I do the exact same thing, but I'm moving that way with a velocity, right? It's like, boom. Like, oh, wait a minute. Like, the ball went up, and I caught it in a different place. For those two things, what can you say about the distance traveled by the ball? Like, physically, in all dimensions, how far did they travel? When I was standing still, right, the ball went up and went, it went that far, however far that is, okay? If I'm moving sideways and I toss it up, the ball goes like that, right? In the second case, the ball had to travel farther. Are we still okay? The light's doing the exact same thing. If you wanted to think of that as like a projectile of light, it doesn't work quite the same. It's like going up, and then it gets caught again by the clock after it's moved some distance. So, in the case of the moving light clock, the light beam traveled further. And we could do the trig and the geometry there and kind of figure out just exactly how far. It's those two hypotenuses. I don't know. If you added those together, you could find the exact distance that it traveled. We're not going to worry about that so much. Just accept the fact that it traveled further in the case of the moving clock. But the problem is the velocity of light is still the same. It can't change. It's forced by nature to be the same. Which means what if I go back and look at this equation? What can you say? So this went up. This one stayed the same. What else has to happen? What's that? T increases? Yeah? So to keep that ratio the same, T has gone up. More time elapsed to allow C to stay the same value. Sit with that for just a second. Question? Yeah. So if you all are sitting here watching these clocks happen, right? And maybe you could like literally see the beam go up and back down and look at the readout and see how much time occurred. in one case. In the one that's sitting here, it's like you'd see it tick 1, 2, 3, light made it to the bottom. The one that's moving with its attached display, something more than 3 has passed on that clock, even though everything is the same about the clock. Okay? Question? Doesn't that mean it's running faster? Think of it this way. Often, like the terminology we use there gets a little mixed. If it takes longer for a second, then when I've measured, say, an hour, maybe only 50 minutes have passed on the thing that's taking longer for each time interval. So we would call that running slow because it doesn't measure as much time in the same period. Sorry, say it again. So more time has passed that we see on that clock. But that's more time, like 5 seconds is now equal to 3 seconds in our time. Like that clock is, in essence, ticking slower, if you wanted to think about it that way. You don't like the terminology? Okay. Are you okay with what's happening, despite the slower or faster terminology? Okay. Yes. Yeah, so you could assume still, and I don't like this diagram greatly, but it's still shooting the light essentially straight up, but then the whole thing is moving. So it's still going straight up and straight down if I were in the clock. It's just from your perspective looking at it, you see it leave here, arrive there, and then hit back there. So the only way it can do that is essentially by traveling along those diagonal paths from your perspective. The distance you would be using from your measurement would be that plus that. And that is greater than just 2D. Okay? So we could say this has gone up to something greater than 2D, and this is now something greater than the T we had before. Okay? Yeah. Mm-hmm. Yeah, it's just like with the ball. Like, I toss the ball straight up and straight down, but if I'm going sideways at the same time, that's not really what you see. You see this motion, but then if you track the ball through the air, you see it go along an arc. Okay? Lots of good questions because I agree this is new and different and maybe makes no sense at all. But bear with me as we take it further. I think we've exhausted maybe the questions there. I don't know. Okay? Let me make sure that there's anything else that I want to say. What if you're riding with the clock? So shrink yourself down, and now you get to like ride on the light clock, right? So maybe you're like hanging out right here. Yay, this is you. Little shrunken down you hanging out inside the light clock. Okay? What do you see the clock do? Right? All you see is essentially like, hey, all I did was throw the ball up, and then I caught it in the exact same spot. So if you're riding along with the clock, you're like, hey, it shot the light up, it went up and hit the top mirror, and it came right back down. So from the clock's perspective, inside the clock's world, it's working just perfectly normal. The thing is, the person in the clock and you people watching the clock move are now in disagreement about what the correct amount of time that passed is. And the reason for that is there is no real correct amount of time that has passed. When people say, like, it's all relative, in this case, literally it is. Okay? The amount of time that's passed is completely based on who's measuring the time and how fast they're moving in relation to other things. Okay? So let's take this a little further and let me give you an equation to show you how this starts to work. Let's see. I said things there. I said things there. I said that. Good. All right. Here's what the equation looks like that will give us the difference in time. And I'll have to describe a few things. So we've got T is equal to T naught divided by the square root of 1 minus V squared over C squared. This is the equation that will tell us the difference between how much time has passed for the clock and for you watching the clock. Okay? So this t is the dilated time. It's the longer amount of time that has passed. And this is the amount of time that you measure at rest. And we should put rest in quotes, because what does that mean? I heard you laugh back there. Like, what is at rest? Like, we're moving right now, right? If you really think about it, we're just not moving in relation to each other. So take a look at this graph. This is a graph of how much the dilated time has changed divided by how much the regular or at-rest time has changed, like a ratio of how much one is compared to the other, based on the speed that the clock is moving. Notice it's all based on a fraction of c. So the maximum the graph ever gets to is at the speed of light. And you can see that the graph is really, really flat, meaning there is no difference in the clock's time and your time unless you're moving fast. Like the fastest that anything we have goes, like lives in a little portion of the graph that's like right here. That's it. Which means that for all practical purposes, like when we're looking at these things happening at normal everyday speeds, the clocks read the exact same time, and we can't really tell. But as you go faster and faster and faster, especially maybe at about 0.2c, you can start to see that line is going up a little bit. And this is all coming from just graphing this equation. Well, all of a sudden it starts to sort of take off. And as I get closer and closer and closer to the speed of light, there's a greater and greater difference in how fast those two clocks are ticking. Okay? What does all this mean? I don't know. What does it all mean? It means we probably need to do a problem. Does that sound reasonable? Yeah. You can't. You just can't. And as we go through this chapter, you'll see multiple reasons why. Yeah. All you can do is really approach the speed of light. And at that point, like if I'm sitting, kind of right there, and I'm watching the clock, it would essentially look frozen. Because compared to me, it looks like time has essentially stopped inside that clock. Now, how do you make that measurement or observation? Like, I need a clock that's going zoom at almost the speed of light, and I'm supposed to be like, what's happening to that clock? You know, I mean, good luck with that, right? Like, but if you could do that, like, you would essentially see just like, if there were people in there, it would just be like, yeah, I woke up some of you, didn't I? You know, I'm sorry. So let's do a problem. You'll start to see how all of this begins to work out a little bit. So, the effect on time. First of all, some terminology. The event. We all know what an event is, but in terms of this chapter and how we're going to do problems, an event is when something happens at a specified location and at a specified time. So we can define its X, Y, Z, and T. Okay? So X, Y, Z, and T would specify an event. We are going to say that something we call proper time, which you may think of as no means being proper after we do a problem or two. This is just terminology. It doesn't mean it's the correct time, the real time. It's just a term to help us keep track of things. Is the amount of time that separates two events that occur at the same location. It's the amount of time separating two events that occur at the same location. And we're going to use this on a problem in just a couple of slides. Before we get to that, though, let me point out, just like we saw on the graph, this effect is really, 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 really small unless the relative speed between the two is really high. Just to give you some idea, the space shuttle typically orbited at around 17,000 miles per hour, which is really fast. That's like 5 miles per second. Yeah, that's actually, like that's moving, 5 miles per second. Where can I be where's 5 miles from here? I don't know, the other side of the Bay Bridge-ish, something like that, in a second. Space shuttle's moving fast. It turns out that is approximately 1/39,000th of the speed of light. in terms of speeds that we're discussing, that is almost nothing, which means that if there is any change in the clocks, which there is, it's really, 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 really tiny. The effect is very, very small. If you wanted to get some idea of the effect that this speed has on a clock, we could say that it would take about 100 years to see a 1 second difference in the clocks. Okay, so the effect is there. It's just very small, and it would take me a long time to see an additive effect that's macroscopic that I could actually measure easily. Okay, so the space shuttle is not moving very fast, and really this effect is only important at high speeds, but it's happening at all speeds. If you're thinking like, oh, this sounds like a hoax, it sounds completely made up, it's like you just invented a clock, I've never seen a light clock. Well, of course you haven't. What is a light clock? I don't know. But you could build one, and then you could have one on your shelf, and then you could like slide it sideways and be like, ooh, look at it go slow. Like, no, it's not going to go slow. It's been repeatedly proven over and over and over and over and over and over and over again that the equation we saw on that previous slide is exactly correct. In fact, all the way back in 1971, which was before any of us were born, so if you're thinking like, ooh, this is like really cutting-edge science, not really. Some scientists put some atomic clocks, highly, highly accurate clocks, think many digits after the decimal point in seconds. They put some on the ground, they put some in some jets, they flew the jets around for a while. And then they brought the clocks back together and decided to look and see if there was any difference in the clocks. There was. And the amount that it differed was exactly as predicted by that equation. Now, if you're thinking, well, how'd they get that right? Like, that's a difficult experiment, right? Because the clocks on the ground, they're kind of moving too because they're going around the Earth. And then the planes are flying. Like, that's difficult. You have to do a lot of calculations to do all the corrections that are there. But still, when the clocks came back down, they didn't have the same time anymore. A different amount of time had passed. They were behind a little bit. So if, I don't know, if you know anyone who's a pilot, or if you've been on a plane before, you're a time traveler. You're just going a little backwards in time a little bit compared to everybody else. Not as much time has elapsed for you as has someone who's stayed on the ground their entire life. Just a little bit, though. It's just tiny, okay? So calculations have been done, experiments have been done to show this is true. But let me add to this a little bit. So first of all, 1971 experiments. Let's write this stuff down. And number two, let's see. Let me get my phone out. And open up Google Maps. And then right there on Google Maps is that blue dot. Right? The blue dot everyone loves so much. Where am I? I'm at that blue dot. That wouldn't work unless somebody does calculations with special relativity. In fact, let's add to this. We'll say GPS requires it. How does GPS work? It's basically velocity, distance, time measurements. There's a bunch of satellites in the air. They have clocks on them that are highly accurate. Your phone has a clock in it that's highly accurate. And essentially, all the satellites are sending down signals from themselves, and your phone picks up those signals. Based on how much time elapsed between when it left the satellite and when it got to you, a distance measurement can be calculated, okay? Well, that's not very good if you just pick up one satellite, but if you get as many as 3, at least, the calculation can be done to find out exactly where you are in three-dimensional space based on your distance to those 3 satellites at a moment in time. The problem is, you're on the ground with your clock, and the satellite clocks are spinning around the Earth, which means that over a period of time, those clocks get out of sync because of special relativity. If the clocks aren't in sync, then all of a sudden you don't really know how far away you are from the satellites, which means that the blue dot ends up in the wrong place, which means that the systems that are calculating where that blue dot should go, somewhere in that code is Einstein's special relativity equations. The corrections have to consistently be made or it doesn't work. In fact, if you were to look at how far off they get Let me just abbreviate special relativity, if that's all right. Predicts that clocks on satellites run behind clocks on the ground. I'm not going to write clocks on the ground. You get the idea. By about 7 microseconds per day. You're thinking like, oh, microseconds. It's noon, I don't really care. Who cares if the clock in the satellite is 9 microseconds behind the clock that's on my phone? It turns out that based on that drift and also general relativity, which we haven't talked about yet, there's another correction that has to be made for that. But basically you get the wrong location after about 2 minutes. So if a correction isn't made constantly, 2 minutes from now, my little blue dot is going to start drifting off to somewhere that I'm not. Okay? It's significant enough that it's not telling you the correct location. How much does that add up to be? That is about 10 kilometers wrong per day. So if you think that this effect really doesn't matter at all, do you want tomorrow your blue dot to be 10 kilometers off? That seems like a bad idea, right? Over time, the little tiny mistakes or errors or differences in the clocks begin to contribute significantly, okay? So we're not just inventing stuff. This is really actually happening like right now, all around us, and our modern technology won't work unless we correct for it. Are you significantly spooked? You should be a little bit spooked. I don't think there's too much that I want to say about this. In fact, I just wrote most of it down, so let's just get rid of that. Yay. If we want more accurate GPS, which is necessary if we're dealing with autonomous vehicles, like we need even better calculations and corrections. But what I really want to point out is that it doesn't just apply to clocks. I'll just let you read that a little bit. Yeah. So it's not clocks. That's not the thing that's changing. It's not like I need to build a better clock that can like keep up with this and not have the effect. It's literally time itself that's different for something that's moving versus something that's not. It's just the clock that's doing an accurate measurement showing us that something different is happening. A different amount of time is passing for something that's moving relative to something that's not moving. When I was growing up, I remember there were all these commercials on TV. Maybe this is how I ended up becoming a physicist. Who knows? There were like these books that they would advertise, and it was like they tried to make it like extra spooky and scary, like The Mysteries of Science. And they would have like these two young people went up into a spaceship and one stayed at home. And, then they would have like Einstein with his hair like float by, this kind of stuff. You get the picture of what's happening. And then the other person comes back and they're like walking on a walker like this and they're all gray and haggard and they're like, what happened to the time? And it's like, I want the books. Can I have the books? I never got the books. It was very sad. I know. Like I should have been given the books, don't you think? But like this is where these ideas come from. And while we haven't really done experiments like that, like we can't really send someone off in a ship at half the speed of light and then bring them back and say like, ooh, how's life? Well, first of all, because we'd all be dead because of the difference in time that had passed. And second of all, we can't create spaceships that move that fast. Just keep in mind, it's time that's changing. Not as much time is passing in the thing that's moving compared to the thing that's stationary. It's not just about clocks. So what we need to do is an example. We're going to start with an example that uses more sci-fi kind of numbers to kind of get across the limits of what could happen. And then we're going to do an example that's a lot closer to home, something that's happening here on Earth right now where we see time dilation sort of extended in a rather large factor. So, in this problem, astronaut Benny travels to Vega, the fifth brightest star in the night sky, leaving his 35-year-old twin sister Jenny behind on Earth. That was a sad sentence, just all around, don't you think? Depressing. Okay. Benny travels at the speed of 0.99 c, so clearly technology beyond anything we have right now, and travels to Vega, which is 23 light years from Earth. We are going to find, well, a couple of different things, but let me just point out some stuff before we get there. First of all, let's say that Benny is on the rocket, and Benny is traveling at 0.99 times the speed of light. 99% of the speed of light, and Jenny is on Earth. Left behind. Very sad. So let's see. Here's Earth, and over here is Vega somewhere. This distance between the two is 25.3 light years. Let me point out that light years, it's got year hiding in there, which often confuses people, and they think, year, that sounds like time. This is a distance measurement, and I want to make sure that you understand how that works. Distance is velocity times time, and what we're saying is that our velocity is c, and our time in this particular case is in years. So we're rewriting this as c times 25.3 years, which is how far light would travel in a period of 25.3 years, okay? So when you see 25.3 light years, think of that as the velocity of light times a period of time, giving me a certain distance, okay? Let's see. So there are two events in this problem. Remember, events are things that happen at a particular time and location. I'm thinking that the first event is Benny leaving Earth. Gets in the ship, off he goes, all right? The second event is Benny arriving at Vega. Lands on Vega, hopefully lands on Vega. Probably just going to fly right past. So let's say the first event is leaving Earth. The second event is arriving at Vega. So let's think about those two events with respect to Benny and Jenny. Remember, proper time is measured by the person where the two events happen at the exact same location. So if I'm thinking about Jenny, like she's on Earth, Benny leaves, and then somewhere way out there, the second event happens. From Jenny's perspective, those happened at two different points, okay? However, from Benny's perspective on the rocket, he's like, I get in the rocket, yay, I left Earth. And then I arrived at Vega. In both cases, they happened where Benny was located, in the exact same location from his perspective. So let's make note of those two things. So we'll say for Jenny, the events are at different locations. On the other hand, for Benny, those events are at the same location. Or for Benny, like the world is a little Benny-centric, right? It's like everything happens where Benny is located. So he left Earth, he arrived at Vega, they happened where Benny was, all right? They happened in the exact same place. So we could say that Benny measures proper time. Benny is the one measuring proper time. So let's see. Part A says, how long does the trip take from the point of view of Jenny? So Jenny is just like, okay, Benny has to go from here out to Vega. I know how far that is. I know how fast he's traveling. I'm just going to do a calculation. Okay, so we could say that A, for Jenny, we are just going to say the distance is 25.3 light years. The velocity is 0.99 c. Velocity is distance over time, so we can rearrange that and say that time is distance over velocity. Don't you love this? This is like first lecture last semester kind of work. That's kind of good, right? Distance over velocity, so let's see. Distance is 25.3 light years. The velocity is 0.99 c. But now we have a little bit of issue with units, so I'm going to rewrite this the way I did above when describing light years, and we're going to say that it's c times 25.3 years is the distance, and then we have 0.99 c in the denominator, and now the c's can cancel out, and we've just got something easy left in years. So those are gone. 25.3 divided by 0.99 is 25.6 years. That's depressing. So Jenny waits a long time, and then one day later, her twin brother arrives at Vega. Okay? How old is Jenny now? 60.6, right? 60.6 years old. All right, so at the point when Benny finally arrives at his destination, she is now 60.6. Let me add a slide, and let's see what's happening with Benny in the meantime. Add page below. What's so funny? I have no idea. What about Benny? So remember that he's measuring proper time. Okay, so what we're going to use in this particular case is this equation. T is equal to T naught over 1 minus V squared over C squared. Okay? And we're going to rearrange that to calculate T naught. You got to like that at least the math in this isn't hard, right? It's just like, yeah, plug some numbers in and you get answers. Fantastic. So, what is T? We just determined T is 25.6 years. And we're going to multiply that by 1 minus V squared over C squared. So that's 0.99C, and that's going to be squared. And we have C squared in the denominator. Somebody get your calculator ready, or maybe all of you. 1 minus 0.99 squared, because the C squareds cancel out. Proper time, you have to figure out which person is experiencing the events in the same place, and then set up the entire problem around that. So the person who's not moving in this problem we're saying is Jenny. She just says, that happened and that happened. There's nothing weird going on for her. But Benny lives inside the moving clock. What's 25.6 times the square root of 1 minus 0.99 squared? 3.61? That's right. Depressingly right. This is literally what Benny experienced. 3.61 years have passed, which means, how old is Benny now? Yeah, 38.6 years old. What? Does he what? No. Unless he looks old as a 38-year-old. I don't know. Yeah. All of it. Yeah, so Benny has literally aged 3.6 years at the time he arrived at Vega from when he left Earth. Also, like, he experienced 3 years. Like, you know, if he, I don't know, had a clock on there where he's like 24-hour days pass, and he gets up and he lives for 16 hours and goes to bed for 8 hours a night and just did a regular routine. He went through 3 full calendar years and apart, and he's like, yay, I'm there. While back on Earth, all of this time goes by, and now if there was a way like to instantaneously, I don't know, video chat with both of them, which, keep in mind that all communications are based on the speed of light, it's a little bit of a problem. We've got an issue at this point. Like, there's no way to, like, simultaneously talk to them. But if you could, well, she's 60, he's 38 now. Things are all messed up and screwy, okay? It's not just the clocks. It is the clocks, but it's also everything physically about how they experience time as well. Okay? No, at this point, if he arrives and says, hey, I think I'll call home. Well, how long is it going to take before that call reaches Earth? It's going to take 25.3 years before she gets that call. So now she's, 80 before she finally gets the call saying he arrived. And now how old? Like, everything is bad. In other words, don't go off in a spaceship at approaching the speed of light. Otherwise, by the time you get back, everybody's dead if you go any significant distance. So it's kind of sad. No. So if he immediately turned around and started the trip back to Earth, again, 3.61 years are going to pass. So now he's about 42, right? But at this point, how many years have passed on Earth? 50 years have passed on Earth. So now his sister is 85, and everything is terrible. Yeah, so now if they came back, right, they would physically see each other and say, but sister, it's only been 6 years. There would be something like that would happen. And she'd be like, I waited my whole life, and you got back just before I died. One might imagine, though, if we had this kind of technology, that people are living longer than 100 years, and they're robotic. I don't know what's going on. Yes? How is it biologically possible? It's possible because nothing different happened in the body. Like, the body just did what the body does at the normal rate of things, and literally only 3.6 years passed. So nothing went different. It's just time itself was experienced differently. What's that? No, he's 38 in every way. He's literally 38. I'm sorry. That's just how the universe works. We don't completely understand it. There's a lot we don't know about what's going on in the universe, and I wish I would live to the day where we could have technologies that would allow us to probe this further. Yeah. Consider that to be the air resistance of this chapter. Yes, if you want to get exact, but let's not worry about it. It's too much. So here's what I want to do. I'm just going to tell you what's happening in this problem, and then we're going to be out of time. We'll do the math on Friday, our last class, because I just want to point out that this happens right here, right now. Above us right now, about 5 kilometers up, there are unstable subatomic particles known as muons that get created because of radiation hitting the atmosphere. They get generated, and they have a very, very short lifespan. They're these particles that are like, poof, they exist, and then poof, they're gone. They die. They decay rapidly. In fact, their entire life is this long. Ooh, let me get the number right. This will make you glad you're not a muon. Oh, I did a bunch of stuff without... Where is the muon life? Oh, yeah, here we go. It's 2.2 times 10 to the minus 6 seconds. So muon's like, I'm alive! It's very sad to be a muon. Muons also travel at this velocity. They're very tiny, so they can go very, very fast. These are experimentally verified facts. They get created there, and they travel to the Earth's surface at that velocity. The thing is that if you do the distance calculation for this, so let's just do how far can they travel in their entire life. Okay, so just velocity times time. So the velocity is 0.995 c, and they have 2.2 times 10 to the minus 6 seconds to go as far as they can, and then they're gone. That means that they will travel 657 meters before, poof, they're gone. Aren't you glad you're not a muon? Yeah? I wonder what it feels like to be a muon. Do they feel joy and sadness? I don't know. Your question. I haven't read the original literature, so I can't tell you exactly. But I would assume at that height, maybe weather balloons can detect the creation and velocity. I don't know. Look it up. No more than I do. That'd be fantastic. Notice how far it is to Earth. 5 kilometers. So they can travel much, much less than 5,000 meters before poof, they're gone. Which means that they should just like get created here and then kind of go boo and then poof, like all gone, no more. The problem is if you set up detectors on Earth, they make it. So they don't have time, but they still get there. Why? It's because, and we'll do this calculation, for the muon, they have 2.2 times 10 to the minus 6 seconds, but for us, 22 times 10 to the minus 6 seconds pass, which means that it's like, oh, cool, there's enough time for them to get from point A to point B, okay? It's a time dilation example in something that's actually existing above us. The clocks are running at different speeds, which means they have enough time to arrive. Go read some stuff. We'll talk about this more, as well as even more disturbing things on Friday, and then the semester will be over. Goodbye. Happy dreams. Yeah, I don't know. All right, so we were talking about this muon. Okay, the muon that apparently arrives at Earth even though it can't live that long, which is a little bit strange. So we had gotten to the point where we said, like, well, for the muon, it has 2.2 times 10 to the minus 6, 2.2 microseconds of life to pull everything together and for stuff to happen. So what I want to say is that there are two events in this problem, and we're going to define the two events, first of all, as muon birth and muon death, just to be a little depressing. So, for the muon, or for the people on the Earth, which thing has these two events happening at the same location? The muon. These two things happen at the same location for the muon. Which means, what time does the muon measure? The muon measures proper time, okay? T naught. So let's make a little list here. We will say, first of all, that's another one. That's just too much. Let's say from the muon's perspective. If a muon can have a perspective, seems kind of unlikely. We could say that it's at rest. It's just sitting there. It was born. And now what does it experience at its birth? It looks with its non-existent eyes and says, what is that planet coming at me? Very, very fast. So we could say that the Earth, for the muon, is approaching at a velocity of 0.995 c. That's not what we see here on Earth. That's not our perspective, but from the muon's perspective, that's what's happening. And then finally, we could say that it's measuring the proper time of 2.2 times 10 to the minus 6 seconds. On the other hand, from the Earth's perspective, we could say that we can use our time dilation equation. And plug in the muon's proper time to find how much time has occurred on Earth during the muon's lifetime. If we can call it a lifetime. It's just not that long. So plug those numbers in. We got 2.2 times 10 to the minus 6. And at the bottom, we've got 1 minus 0.995 c squared over c squared. And the c squareds cancel like they always do, and then we just have this radical in the denominator, which is going to end up giving us a larger time, and you'll see that it's 22 times 10 to the minus 6 seconds have passed on Earth. Which means that with this additional time, and at that velocity, notice that's a factor of 10 larger than the muon's lifespan, it means it can travel 10 times as far, which means instead of this value, based on this, we see the muon travel 6,570 meters of distance, which is larger than 5,000 which is why they arrive at Earth. It's all because the time is dilated from our perspective, and the muon can live long enough to crash into the Earth. The muon doesn't have a happy life, all right? Either it's just going to die and go poof in space, or it's going to crash into the Earth. We're going to look at this from another perspective in just a second, okay? What I want to know at this point is just like time calculations, figuring out which one's proper time, which one's not, plug the numbers in. Just nod if you think things are kind of okay there with our two examples. Kind of roughly okay, all right? So let's skip over these. Actually, let's do this one just because it's bothersome. An astronaut moves away from the Earth at close to the speed of light. How would an observer on the Earth measure the astronaut's pulse rate? Yeah, it's not 4. 4 is sad. Yeah, that's just wrong. Okay, so the astronaut would just be like, normal pulse, 65 beats a minute, life is happy. But someone on Earth with some sort of weird fancy telescope where they can look out and peer into the spacecraft and like watch the pulse monitor beep or whatever would see something going much slower because slower time on the moving thing compared to dilated time on Earth, okay? Let's see, we're skipping that one, which brings us to length contraction. Remember we said that, well, velocity is distance over time. So if something weird is happening with the speed of light and the fact that it's a constant and it's this constant maximum value, that distorts the other two things in the equation. We looked at the time part of it, but we haven't looked at the distance or the length part of it. And we will see that it has a weird effect as well. And really, these are like two different sides of the same coin in a way. These are interrelated effects, and it sort of depends on which perspective you're coming from, which one you notice more. So length or distance contraction. We can say that a moving object, why did I write "and moving object"? That's just wrong. Grammar police on myself. A moving object is shorter than an object at rest as measured by the observer at rest. And again, what is at rest exactly? Be a little careful there. What I'm trying to say is that if we were just sitting in the classroom and all of a sudden a meter stick just went and flew across the front, first of all, we should all leave because scary. I don't like the sound of any of that. And let's say that the meter stick is traveling at an appreciable percentage of the speed of light so we can notice the effect. And we measured the meter stick. It would no longer be a meter stick. It would be something shorter than a meter stick. It would shrink. Its length would be contracted from our perspective. This contraction only happens along the direction of motion. So it's helpful to consider something like a meter stick because if it's moving directly horizontal, it shrinks along the meter stick direction. The other dimensions aren't getting any smaller, okay? The length is contracted. So now we have a new definition of proper. Proper length is the distance between 2 points as measured by an observer at rest with respect to those 2 points. What in the world does that mean? Ew. Okay, so maybe I'm trying to measure the length of the meter stick. Okay, as it flies by, well, I'm not at rest relative to those 2 points, right? If you just imagine the two ends of the meter stick, they are always at like a different distance from me. So those two ends of the meter stick are not at rest relative to me. On the other hand, if I ride the meter stick, which kind of sounds like fun, right? I'm like sitting on the meter stick, whee, like this is a good time, and I'm right in the middle. The back of the meter stick is exactly a half a meter behind me. The front is a half a meter in front of me, and that's not changing as we move. I'm at rest with respect to the front and the back of the meter stick. In that case, someone riding the meter stick is measuring proper length. Okay? Blah, 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 blah. That was more of a comment, I think. Yeah, yes, I'm going to ride a meter stick. I don't know. So if we take a look at Benny and Jenny once again. So back to Benny and Jenny. Don't you wish we could do demos with this material? Yeah, that'd be fantastic. All of a sudden, like, people are getting old at weird rates, and, like, don't take that class. You will age. And not because it's boring. Like, you know. So notice, here we've got the spaceship. the Earth's observer's point of view. Remember, that was Jenny. So she sits at Earth. There's Jenny. She's on Earth. And she's like, Vega is a long way out there at 25.3 light years. And poor Benny is on the ship traveling away from her at that speed. Okay? Nothing really weird is happening there except for the fact if she could observe the spaceship, it would be a little shorter. If she could observe Benny, and maybe Benny is like on the ship riding it like this, Benny's getting a little thinner as well. So, no comment about myself on that one. So, also Benny is a little shrunk in some perspectives. On the other hand, if you are in the ship, if you are Benny and observing what's happening, well, in this particular case, you might imagine that he is measuring proper length, and he doesn't experience anything like with his ship weird happening. What he sees is like everything around him is moving. Vega is rapidly approaching from the front, and, well, Earth is rapidly leaving at the back. What is contracted in this particular case is actually the distance between those two worlds. How does all this fit together? Remember that Benny only took how long to get to Vega? Does anybody remember? 3.61 years, I think, to travel to Vega. So we could say that velocity is distance over time, or we could rearrange that for distance, which is velocity times time. And we know that he's traveling at 0.99 times the speed of light. And we also know that the time was 3.61 years. If you plug those numbers in and see the distance that he traveled based on that, you will quickly see that it's not 25.3 light years anymore. Instead, it's 3.57 light years, which you can see is down there in our diagram. So from Benny's perspective, like, time wasn't weird. He's just like, I got here fast. But he also got there fast because he didn't travel as far from his perspective. The space, the physical distance between those two worlds, as he looks out, like went and shrank down because he was moving so fast. How creepy is that? Okay? Just hold it till right at the end. If you can hold it in, then we can get through the rest of this and life will be happier, I think. So what we can say is that the distance between Earth and Vega contracted. And if you think about it, it was because it was moving from Benny's perspective. So it doesn't have to be a physical thing like a meter stick that's shrinking. It can be literally space itself if it appears to be moving from your perspective. So let's imagine me riding the meter stick again. Ooh. First of all, it sounds like fun. I wish I could do this, right? As I travel by you on the meter stick, you would see both the meter stick and me compress some in that direction. What I would see is the width of the classroom get smaller, all at the same time. It just depends on which perspective you're looking from, okay? So there's an equation for this one. You're going to need this for the homework, so I should give it to you and show you how it gets the answer we just got. And it looks exactly like what we had for time. Whoops, that shouldn't be in the denominator. It doesn't look exactly like what we had for time. It looks similar. There's proper length, L naught, and it's multiplied by that same factor, which you may have noticed your homework calls gamma, because it keeps coming up over and over again. It's just a way to simplify the equations a little bit. So let's use this equation to see if it gives us the same result as we saw just sort of logically thinking through it on the previous slide. So the proper length, 25.3, is measured by Jenny because she's keeping the same relative distance to the 2 points in the problem. Okay? For Benny, they're moving. He's not always the same distance from Earth and Vega. Rather, it's Jenny. So this is measured by Jenny. And we can multiply that by 1 minus, or square root of 1 minus v squared over c squared. And what were those numbers again? 0.99c squared over c squared. And you'll get 3.57 light years. So notice how these disagree. Jenny measures proper length, but Benny measures proper time. So don't think that those are always going to go in alignment with each other. Most of the time they're backwards. Different perspective is giving something different. Take a look at the graph. That is a graph of that equation. And they're just showing what the length of 1 meter does as something of that length goes faster and faster. So imagine this is just a graph of what happens to our meter stick. Ooh. If it could go all the way to the speed of light, it essentially contracts to nothing. Or at least it's approaching that if we could actually get to 1 times the speed of light. That's a little disturbing, but it's also a good way to sort of trim up, I guess, if, sure beats exercise. Ugh, I hate exercise. I need to exercise this summer. No, I won't do it. So what about the muon? What did the muon experience? Notice they're showing how length contraction is observed here. From the Earth's perspective, that is proper length. It's like, ooh, the muon is created 5 kilometers up here. I'm down on the Earth. I'm staying at rest relative to those 2 points. But from the muon's perspective, Earth is approaching, and that distance is contracted. So if I use the exact same equation, what you're going to get is that the muon observed only traveling a little under 500 meters, which is sort of how the quandary is resolved. Like from the Earth's perspective, well, there was more time, so the muon could arrive. From the muon's perspective, I didn't have to travel as far, so I was able to hit the Earth. Okay? So it's 2 different ways of looking at the exact same thing. One is experiencing time dilation, one is experiencing length contraction, so that you end up getting the same result and there's not a paradox of sorts. Okay? Whew. Hello. We're all just saying hello. I was in the middle of taking a breath because I'm talking too fast. So let's move forward and see how this all sort of fits together. Whoa, going over here. So we can no longer just add velocities. We saw this in one of the multiple choice questions on Wednesday where it was like things are approaching each other at 75% of the speed of light. I can't say that the relative velocity is 1.5 times the speed of light because seemingly nothing can quite get that fast, which means that we now have to add velocities differently. And I'm just going to give you the equation and show you a little bit about how it works. Okay, so the equation looks like this. V sub 2,3. This is the velocity of object 2 relative to object 3. And we're only going to look at the equation in 1 dimension with 3 objects. I will let your imagination run wild with how much more complicated it could get if I decide to try to do this in 3 dimensions with vectors. Yeah, things get a little bit messy. So we're just looking at 1D with 3 objects moving in relation to each other. Velocity of 2 relative to 3 is equal to v21 plus v13. By the way, you might notice if I were to just stop right there, that's what we did in Physics 8A when we were dealing with relative velocities like a person on a train and we added together how fast the velocities were. That was the equation. And it works just fine for regular velocities. But as velocities get faster, we have to put this very messy term in the denominator. Let me make sure I get it right. 2113, 2113. Good. Okay, everything is there. So what do all these mean? Did you write it down? Say yes. Say yes. Say it again. Yes? You're lying. I don't know. Maybe you did. Spaceship, space probe, asteroid. So notice we're saying that from the asteroid's frame of reference, there's a spaceship approaching at some velocity, and they shoot a missile or a probe or something. And now I see both of these coming at me with certain velocities. So notice it's the velocity of the spaceship relative to me, the asteroid, and the velocity of the probe, number 2, relative to me. Those are two velocities of things that are coming at me. If, on the other hand, I'm on the spaceship, now I'm at rest, but I shot a probe out, so it has a velocity of the probe relative to me, and also the asteroid is fast approaching, velocity of 3 relative to 1. I know it's an awful lot of stuff, all right? So first of all, notice one thing. What if C could be faster? So what if C wasn't like this maximum that we've been talking about, but rather C could go to infinity in this equation? What happens to the equation? So make this denominator really, really big. So this becomes 0. And then I have 1 plus 0, which means I just have the numerator that's left. So in other words, if C could be infinity, this equation would reduce to just the classical result. This is the old way of thinking. In other words, it's specifically because there's a max for C that's making things weird. It's not because C is so fast. It's not because it's this crazy high number. It's because it has an upper limit. Putting an upper limit on it in that equation forces it to be this weird thing instead of what we learned about in Physics 8a. All right? So that's the first thing I want to point out. Let's see. The second thing. What if the probe was light? So think maybe not a missile, but maybe they shoot a laser. Okay? So we know the velocity of the probe if the probe was light. It means that the velocity 2-1, which we see over here, like I shot out the probe at the speed of light. So I'm going to know that that velocity is c. And let's see what happens to the equation. So then we're going to have v23 equals c plus v13 over 1 plus c times v13. And I'm just plugging in c everywhere we see v21 over c squared. And what does that simplify to? So that c cancels with one of those. And then we could rewrite this by factoring out a c as c times 1 plus v13 over c over 1 plus v13 over c. Huh? What? V23. What is V23? V23 is how fast the asteroid sees the beam of light coming at them. Remember we said that no matter what reference frame you're in, c is c. Light is always traveling at c. Notice, I'm in the spaceship and I'm like, Choo! I shot a beam of light and I saw it leave at the speed of light. The asteroid is sitting over here, and even though like the spaceship was moving and it shot this thing out in front of it, it still experiences the light coming at it at the speed of light. So this equation takes care of that concept that we saw back in one of the earlier slides, all right? There's one other thing. What if low velocities? Remember that these equations need to sort of simplify back to like regular stuff if I don't have a high velocity that's happening. So let's just say, let's let the ship be moving, which is going to be v13 at 25 miles per hour. Ooh, that is one slow spaceship. And let's say let v21, which is the probe, be 15 miles per hour. So much more terrestrial speeds at this point. If you plug those in, notice what happens to the equation. If I take those two numbers and multiply them here, and then put them over c squared, I basically have a tiny number over a really big number. This is essentially 0. And then all of a sudden I have 1 plus 0. And we're just adding those two things again, which means that you're going to get what? You would get v23 equals 40. And it would work exactly like you expect if the speeds are small enough. okay? So this equation, even though it seems a little convoluted, it's got stuff kind of all over the place, it like deals with all of these cases that we would expect it to, all right? Which brings me to this graph. Whew, this is a weird one to look at. So let's imagine that we have a rocket on Earth and it's super powerful. And every time we just go like for 1 second with the rocket, it increases our velocity by 1/10 of the speed of light. That sounds fantastic. Maybe one day we'll have something like that, okay? There's going to be a little bit of a problem. You can imagine when I'm not going too fast, it's like I fire the rocket once, boom, it puts me like right here. I fire the rocket twice, boom, I'm going at 0.2 the speed of light. That can't indefinitely continue because eventually, like just after 10 firings, I'm going to hit the speed of light and then go beyond it. I can't go faster than the speed of light. Nothing's going to happen, all right? Instead, what's going to happen is as I get closer and closer to the speed of light, now it's like my firing of the rocket doesn't do me as good, which means like maybe this firing from 10 to 11, like now maybe it only gets me like 0.05 extra velocity. And now as I go faster and faster, each one of my rocket firings, which haven't changed, it's the exact same amount of strength, gets me less out of it. It gets less acceleration out of it because I have this upper limit on my velocity. Which means at some point, like I reach this point and I could just fire my rocket for all of eternity and just never really go any faster, which is kind of depressing. Why does that occur? That occurs because of what's on the next slide. Let's revisit last semester. Do you remember collisions? Yeah, a little bit maybe. I feel like part of what I should do when I say that is like I should just run into the wall. Be like, remember collisions? Rah! Boom! And you'll be like, yeah, I don't remember that, but I do remember collisions. We talked about a particular collision where we had like a really large mass that was moving and it collides with a little one that's not moving, that the little one ends up going twice as fast as the big one was going. This was like one of the extreme cases we looked at. The thing is, you start to run into a problem if like that first one is moving at 60% of the speed of light. My collision fails because like this thing can't, like the little one can't go at 1.2 times the speed of light. It's just not going to happen. So what is really going on is that momentum has also changed, or momentum, if you prefer your momentum that way. P equals mv. Here's what's happening with mass. Mass gets larger as you go faster. Mass gets larger as you go faster. And this is, again, from the perspective of a rest observer. So think about poor me on that meter stick once again. Right? I'm flying across the room, and let's say I accelerate rapidly, so I'm approaching the speed of light by the time I hit that wall. Ouch. That's sounding just bad all around. Well, what you're going to see happen is a couple of different things, right? First of all, we already decided that things are getting shorter in that dimension as I go faster. I'm experiencing the walls getting closer together. But also, as you look at me, like, you're not going to really see any difference, but somehow my mass is also growing, all right? Getting more and more heavy as I also shrink this direction. This is, yeah, you laugh because it's a convoluted thing to imagine. It's not that I'm just getting fatter. It's just that I'm like getting denser in a weird way. The mass is increasing according to this equation. So this mass is equal to m naught, which is known as the rest mass, over the square root of 1 minus v squared over c squared, once again. Or in other words, as v goes to c, mass approaches infinity. And now all of a sudden it starts to make sense that if you keep firing the rocket, you get less and less out of it because you're trying to push a whole lot more mass. The same force doesn't get you as much acceleration. And then, of course, if I plug in v equals 0 in that equation, you should see that m just equals m naught, the regular rest mass. So you start with the mass that you have at rest, and that gets larger and larger, approaching infinity as you go faster. So you could think of this as the relativistic momentum. It's the exact same equation, except mass has a little bit more going on. Instead of just being the rest mass, which is what we've always used, it has this other equation that accounts for the mass growing larger. Which means that, weirdly enough, if you do work on an object, right, like pushing the rocket with a big explosion with all this thrust, well, that work is transformed into energy, but in two different ways. Part of it is going to increase the velocity, but part of it is going to increase the mass. Just due to conservation of energy, it has to go somewhere. So you might imagine that what happens at lower velocities, primarily, if I do work on an object, I just speed it up. But when I get to the point where, like, I can't really speed it up anymore, like, it starts to switch over. There's, of course, a combination as I go faster and faster. But this is a larger effect at high velocity. Instead of making it go faster, I push on it and just add to its mass. So talk about a completely ridiculous thing to try to do to a rocket. Like, I want the rocket to go faster, but every time you push on it, all you do is make it heavier. Also, be nice to your friends. Don't go pushing them around. Think about what you're doing. You're not only knocking them down by increasing their velocity, but you're making them a little bit heavier. Just a little bit, okay? So, and there's no way to get that back. I'm sorry. Like, that's just how it is, all right? Which brings us to this equation and means that mass must be another form of energy. If I do work and I can turn it into kinetic energy, but I could also turn it into mass, remember, work is just like how we transfer energy between things. The logical conclusion is that mass is another form of energy, which means there is something known as relativistic energy. And it's going to look pretty familiar. E is equal to m naught c squared over 1 minus v squared over c squared. Or I could take this whole thing and just rewrite it as m. Ooh, and finally, that famous equation that maybe you've heard about your whole life or seen your whole life, well, that's where it comes from. It's falling out of relativity in a way, and this increasing mass with velocity. Also, talking about those books I saw as a child that were on the commercials that I wanted to see, you know, this was another thing that was happening, like E equals mc squared is like twisting and floating by, you know, together with Einstein going the other direction. You can imagine this commercial. Yeah, so I feel like this is one of those equations that's just always been there, even if I had no idea what in the world it was about. So again, if we say V is equal to 0, then this thing just becomes E is equal to the rest mass times c squared, which is known as the rest energy. Unless you think that when you're not moving, your mass doesn't have a lot of energy, remember that c is a really, really big number. So when you're sitting here like really sleepy in the afternoon and you're thinking like, I've got no energy, there's nothing I can do, you are full of energy. If there was a way for us to like take your mass and just boom, let's like turn you into just raw energy somehow and use that in some other way. First of all, I'm sorry, because you're not coming back from that so well. If we do this calculation, say, on a 0.12 kilogram apple at rest, and of course, if it's moving, then, well, it's got even more energy. This would be equal to 1.1 times 10 to the 16 joules of energy, which would be enough to power the United States for 1 hour. If you do the same thing to a banana, the earth is destroyed. Just so you know. It's like the evil opposite of an apple. Okay, so you can get some good out of an apple at rest. If we wanted to convert that another way, this would deal with a 100-watt light bulb for for 10 million years. There is a lot of energy that's bound up in matter. So that's why nuclear forms of energy are so interesting, where we're taking just a tiny, 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 tiny little microscopic piece of matter and converting it into energy, and then, right, you can power things, you can blow things up. You can have things like the sun. Tiny little conversions of mass into energy give us a whole lot of energy. And that ends special relativity. Oh. Let me pause there for questions. Does anybody have anything in there where you're just like, what about this? Yeah.
So you're talking about the relativistic addition of velocities and how if we kept pushing something, the mass would continue increasing.
Yeah.
Then for that graph, why is it asymptotic? Why doesn't it start decreasing because the mass continues increasing to infinity, but the velocity has a maximum?
I think for the exact reason you said, the mass is, as the mass gets bigger and bigger, that's what's limiting the velocity. So I push and I don't get velocity increase, but I do get mass increase, which thereby reduces the amount of velocity that I can get at the same time. So the mass can keep growing and growing and growing, and that puts an upper bound on the velocity, and you never quite get to see, no matter how hard you try.
But why doesn't it go downwards after that?
Why doesn't it go downwards?
Because the mass keeps increasing, right? But
Yeah.
the velocity stays at this upper limit. So if the mass continues increasing, it shouldn't go down. Shouldn't hit that maximum point and go downwards.
Yeah. I don't know. Let's talk about that after class. That's a good question. Anybody else? All right. I've scared you, haven't I? Now you're just like, no questions. Therefore, he has to finish the work, and then life will be sad if he doesn't. Let's talk about general relativity. Maybe that's the real thing. You just want to hear what general relativity is. Yes. Yes. Some of you do. Okay. General relativity applies to the other case. It deals with gravity in a broad sort of way. And instead of dealing with inertial reference frames, ones that aren't accelerating, this is dealing with accelerated reference frames. So those times when it's non-inertial. So think of this as it's like general relativity deals with reference frames of any type, and special is like a special case where we force things to move at a constant velocity. Okay, it's like a subset. So here's the thing. We have another principle of equivalence, another equivalence principle, which is that no difference should be detected in physical experiments conducted, A, in a uniform gravitational field. That's what we're in right now. It's like gravity is pulling with an exact acceleration right now, and it's staying perfectly constant at all points in this room, versus in an accelerated reference frame. I shouldn't be able to tell the difference between the two. So here we're not dealing with just two different things, one moving at constant velocity and one not, but rather one case where I'm in gravity of a certain gravitational acceleration and in an accelerated reference frame with the exact same acceleration. All right? Here's the way we're going to illustrate this with a person in an elevator next to a tree. Wow. I can't even comment on any of this. I don't know what's happening. All right, so this person is just on the earth in a box. She's not dead and alive, so don't worry about that part of it. Instead, she's just in a box, and she drops something, looks just like a ball. I thought it was an apple for a second, but no. She drops a ball. She does measurements, as one does when in a box on Earth, and says, look, acceleration due to gravity is 9.8 meters per second squared. Okay? The reason we have her in a box is because now we're going to transport her to space and turn her into another person, apparently. I don't know why. So now the box is just hanging out in space and not accelerating. If you let go of the ball, nothing happens. So you would say, well, apparently there's no gravity. Nothing's going on. There's no acceleration. I measured no acceleration. On the other hand, if you took that exact same box and made it go upwards at 9.8 meters per second squared, well, think about what happens to the ball now, right? It's like, okay, here I am. I'm standing. I drop a ball, but all of us are accelerating upward. Not the same velocity. That's the common mistake. It's not just moving up, but it's speeding up as it goes up, okay? That ball wouldn't stay right here. Instead, it would speed toward the bottom because like the bottom is approaching it, okay? Which means that this person, if they couldn't see outside, they would just be like, I must be on Earth, 9.8 meters per second squared. They can't tell the difference. They're like two ways of looking at the exact same thing, okay? An accelerated reference frame and a gravitational field of the exact same value for G or A, you can't tell the difference doing any physical measurement. And that means everything. That's not just dropping a ball. That literally means like you would feel like, I feel my normal weight. Like this is exactly how I feel on Earth. Everything would feel exactly the same. So what that extends to is that means that if I do an experiment with light, why has it always got to come back to light? I should get the exact same results that I would on Earth. So the way we're going to think about this is in the non-accelerated elevator, if this random person shoots a beam of light out of a flashlight and it's not accelerating, it should just go straight across and hit the wall. Seems reasonable. But if the box is accelerating upwards, then you might imagine if you slowed things down, the light beam leaves, but now the whole thing is accelerating upwards, which means that the light's not going to hit straight across. It's going to hit down just a little bit. You have to kind of stretch your mind there a little because light's fast. It's hard to imagine it being like, ooh, now I'm going to hit a little lower on the wall. But if you did that experiment, that's what you would see. You'd be like, wait a minute, I aimed there, but it hit a little lower on the wall. Okay? Which leads us to the idea that if I did that on Earth, we're going backwards now. We just said that these two things have to behave exactly the same. So if I did the same experiment on Earth, where I have the exact same acceleration or gravitational field, the light should bend by the exact same amount. Now, we don't generally notice this because it's a tiny, tiny, tiny little effect. Okay? But the idea is that gravity must have an effect on light. Why would we even think that gravity could bend light waves? It seems so counterintuitive. And the problem is, we've done a lot of experiments and proved it to be true, such as this. Gravitational bending of light. Experiments have been done where we look at stars in the sky, and sometimes we can see stars that we know are directly behind the sun. And it's like, why, like the sun just moved to cover that up, and yet I can still see it on the side. It's like it moved somewhere else in the sky. Well, we're pretty sure that the star didn't just go like, I think I'm going to be somewhere else because I really like to look at the Earth. It's like, get out of the way, son. Like, look at the Earthlings down there. Don't they look sad? No. Instead, what's happening is that light leaving that star in all directions, light rays pointed straight at the Earth can't get there anymore, but ones that would generally miss the Earth and we wouldn't see are bent by the sun's gravity and still get to us. Many astronomical observations have been done showing that this happens over and over and over again. Even more long-range things like, let's skip over that one, like looking at distant galaxies. Like here is a case where there is one little galaxy that's happening there, but we actually see multiple of them kind of laid out, because what happens is light goes around a galaxy that's between us and them, and we see it like duplicated in the sky because the light is bending around that galaxy from different directions. And that's what the actual image of the thing looks like when that other galaxy's in the way. It's like, boom, there's multiple. And then it goes out of the way, and it's like, well, now there's not. Well, it can't just spontaneously spawn additional galaxies. Instead, we're just seeing multiple images of it, all right? And you may remember, there's no time to talk about all this. Remember that thing? Michelson's experiment and all of that? That's where all of this ties in. The idea that gravity bends light because gravity is actually bending the space that the light is traveling through. Yeah, what does that even mean? It means that as you walk around, like there is space around you, right? Like stuff is all right here. Your mass makes a little indention in space. It's tiny, it's undetectable, but it's bending it just a little bit. When I deal with something like the sun, it makes a huge indention in the fabric of space, which now that starts to make sense. If I imagine like a light beam that's going this direction, it's like, whoa, and then it bends because the space it's traveling in is actually bent. So it's not really that, I don't know, light is attracted by a gravitational source. It's still going straight. It's just that the thing that it's traveling through is now bent. And it follows that curve, which is kind of a cool way of thinking about things, and also really hard to wrap one's brain around. The thing is, we've now actually started doing physical experiments with LIGO that are detecting this stuff happening. So it's not just that we see light rays that are coming from a different location in the sky because of gravitational bending, but now we're actually detecting these little ripples in the fabric of space as measured with the Michelson experiment, just sort of writ large, which is kind of awesome, kind of cool, and I love it all. Don't you? That's the end. We made it.